Awesome. Can you hear me?
Yep, sounding good.
Okay, let me share my screen. Oh, it says host disabled.
While Derek's getting his technology all lined up, I'll just
Oh,
uh, remind you all, if you haven't looked at the syllabus since beginning of class, the next 2 weeks we're going to spend on interval data. Um, so this is an area that's going to be an increasing area of opportunity. A lot of other IACs are doing this work regularly just by nature of their utility and the data they get. So thank you, Derek, for putting together what you'll start us off with today, and then we'll have another session related to the same topic and follow up next week. So all yours, Derek.
can you see my screen?
Yep, looks good.
Okay, great. So yeah, like Julie said, today I'll be presenting on interval data analysis. And before I really get into interval data analysis, I'm going to talk about electricity billing structures because that is really the motivation of a lot of what we do with the IAC, trying to save energy, but ultimately we're really trying to save these companies money. So really, really broadly, without getting into too many details, um, electricity billing structures are as follows. They happen on monthly time intervals, and they're oftentimes broken into on-peak and off-peak designated times. On-peak times are more expensive. That's usually could be like 7 a.m. to 11 p.m. on weekdays, and then every other time, like weekends, nights, holidays, are less expensive. And then you break everything down based on peak or off peak. Um, that includes electricity rates. So you have on peak electricity rates. Electricity is more expensive during weekdays in the middle of the day, and then less expensive during off peak hours. And then this is also relevant when we're talking about demand charges. So I'll get into more details on this, but demand is the maximum 15-minute power draw during on-peak hours for a bill. And a facilities charge is similar, but it's just the maximum power draw during any time interval. So these kind of hit the major aspects of a bill of an electricity bill, and now I'll slowly get into how looking at 15-minute interval data can help us look at these different aspects of a bill. Before I go one step further, I just want to talk about demand units because it's a little bit different than electricity, and the way it shows up with Rutgers and IAC portal is a little bit confusing, I think. So electricity bills like Rocky Mountain Power will record or will charge for power on a dollars per kilowatt basis. So every bill the facility gets charged for their maximum 15-minute power draw during on-peak hours for demand, and that's a dollars per kilowatt here. Instead of demand charge, it shows up as power charge. But you can see it's $14.62 for the maximum power draw they have. And then in our reports, when we're showing what the demand savings are for each AR, we report it in kilowatts per month. Most people have seen that, hopefully. But the confusing thing, and I reached out to Julie about this, is that the portal uses kilowatt months per year for their total demand savings for the year, for annually, and I don't have a good explanation for that. And Julie just told me not to worry about it too much, and I don't think you guys should worry about it either. But basically, that's a way to summarize the total demand savings for the entire year. So you can just, if you have the same demand savings every single month, you can just multiply that number by 12, and that'll give you the demand savings that you will enter into the online data portal. All right, so now I'll get into the actual interval data. So what is interval data? It's the average power draw over a designated time period. Usually that's 15 minutes. Could be an hour, could be 30 minutes, but it's selected based on what's most useful for the facility. 15 minutes is selected because that is what shows up for the billing. The maximum 15-minute power draw. So if you had hourly intervals or 5-minute intervals, it wouldn't be very useful if you're trying to minimize your bill. But what it also does is it allows you to look through a lot of noise. So if you look at the chart in the bottom left here, you can see average power draw for a facility on 1-minute intervals for 60 minutes. But if you look to the chart in the bottom right, you can see what it would look like for the average power draw for 15-minute intervals. And so there's a lot going on in the chart in the bottom left, but the one in the bottom right is actually what's relevant for billing. So that is kind of the level of detail we're really interested in seeing here. This is quite contrary to how it's presented in bills. If you look over bills, which I know a lot of people have done, you'll see that there's only one single data point on the whole bill for the maximum power draw of the facility. And so it just has one value. The peak power draw for this month at the facility was 1,000 kilowatts, for example. And it's pretty hard to do anything with that information if you don't know how it fits into like the grand scheme of their power consumption. So by averaging for 15-minute power draws, we can see kind of this pattern emerge and see what kind of how their process lines up with their power draws.
Hey, Derek, can I ask you a question?
Yeah.
So if you look at an hour of data like that, do they look at the first 15 minutes, then the second, the third, and the fourth, like in 4 even blocks? Or do they look at that whole set of data and say, whatever is the highest 15-minute interval here, we're going to charge them for? Or do they break it up into the very discrete first 15, second 15, third, fourth 15 minutes?
Glad you asked that. I actually don't know. So I'll defer to Julie if she knows, but I think it's starting at the beginning.
It's actually a mixed bag, Michael. I don't think I've worked with a lot of utilities that have the capability to collect that much. Like the more common situation is the utilities have less than the 15-minute averages. It's not common that I've seen anyway that they collect minute by minute data. So there's actually probably different techniques where they use their data to set that maximum peak. I would say it's not universal.
Okay.
Yeah. I'm glad you asked that. So for this presentation, I've assumed that it's like the first 15 minutes and the second 15 minutes and third 15 minutes. But you're right. If it's a rolling average of 15 minutes, then it's a little bit different. So I guess that's a good thing to keep in mind for the rest of the presentation, and I guess it's not relevant for every case. All right, so if we have this data, why are we really looking at this data? So we want to identify some ARs, some assessment recommendations in the process, and come up with some, based on looking at the data, ways we can shift it around and save the company some money. So if we're looking at 15-minute interval data, we want to present the data in a way that's as easy to interpret as possible. So one option to do that is presenting it in a table like this. Does anyone have any favorable or unfavorable things to say about presenting data, 15-minute average data in a table?
I feel like that could be good if you just highlight like the high and the low. But other than that, it's really difficult to understand, especially when you got a bajillion digits on it.
Yeah, I'm glad you mentioned that. Yeah, first of all, presenting a bunch of extra quote unquote significant figures is really useless because It's just, maybe it's just a factor of averaging numbers. I know this is there just because I used a random number generator and purposefully didn't lower the number of digits, but looking at this, it's really hard to see immediately where the peak is. So, and this is only 10, 15-minute intervals. For a whole month, you're looking at a lot more than that. So trying to sift through data in a table when you're presenting it to your teammates or your colleagues, we want to make it as easy as possible to see the patterns that are emerging in the data. So if you ever have the chance to look at this data, and the first thing you want to do is, put it in a form that's easier to use. A second option is plotting points and connecting the data like this. Does anyone like or dislike this data presentation for 15-minute intervals?
I'll make a comment, Derek.
Yeah.
I like it, but the problem is between 3 and 4 or 4 and 5, it gives people the impression that it was just a direct ramp, things like that. So you got to understand that there are distinct data points and that the lines in between don't mean anything.
Yeah, exactly. So, if you have this 15-minute average data and you're connecting the points, you're implying that what's happening between there is really actually happening. So like Blake said, the data points show you kind of this pattern. You see this higher peak in the 5 or the 6 to 8 range, and you see that there's a lull outside of that. But when you connect the points, you're saying, oh, the average power draw at 4.5 is 40 or something like that. And that's just not what the data shows at all. We have the average power draw at 4 is 3.9 or 4, and the average power draw at 5 is 62. And trying to assume anything in between there is detracting from our ultimate goal. So just the way I would present it, this is up for you, but the idea is to make it as easy as on you as possible and to share the information as quickly as possible. So I would share it as a bar chart because this is what the data actually shows. And it doesn't smuggle in any additional information that's not really there. So if you have the luxury of having 15-minute interval data and you can plot it and you want to start looking for patterns, I think you want to do that, especially because looking at tables versus charts is really, really different when you have hundreds or thousands of data points. All right, so now I just want to look at this small sample. So this is 10, 15-minute intervals of average power draw. And this is small compared to like a monthly data set where you'd have 30 days approximately for 24 hours. And each of those hours is broken down into 15-minute intervals if you're looking at it that way. If you're doing a rolling average, then it's going to be a little bit different. But if everyone wants to either pull out a calculator or guesstimate or pull up an Excel spreadsheet, I think you guys can pretty quickly come up with answers to these questions. So the first data point I want is, what is the total power consumption for this chart that I'm showing here?
You can multiply the average power by the amount of time and then add everything together to get the kilowatt hours.
Yeah, exactly. We'll wait for it. If you get within 20%, we'll move on. I think if you just look at, you can just average it and multiply by the time interval if you want, like Mateo said.
Is
when
it
you
something
take
like
this?
80 kilowatt hours? Oh, it's not what Quinn got.
You guys got 80?
I got 80 just by guessing. That's
Okay.
probably not right.
I mean, it's not, okay. What was your thought process? You're on the right order of magnitude, and I think that's good to look at the data and say approximately what's a good guesstimate. How did you come up with 80?
So I looked at the data. I kind of assumed that the average power draw here, something like 30, 35 kilowatts. Then we can see that it's for 2.5 hours. So 2.5 hours times an average kilowatt of 30 gives you approximately 80 kilowatt hours.
Awesome. Thanks, Conrad. Yeah, so that's totally, so there's kind of two ways to do it. I'll walk through maybe the more roundabout way of doing it and then talk about kind of how Conrad did it, which is maybe quicker. So if we have this 15-minute interval data, we know that 15 minutes is 1/4 of an hour, and we have the average power for each 15-minute interval. The power, in this case with units of kilowatts, times the time interval. We want hours because kilowatt hours is the relevant metric for energy for billing purposes. We want to multiply the power of each interval times the time of each interval. So the first interval is approximately 42 kilowatts times 1/4 of an hour. So that first interval draws 10.5 kilowatt hours of energy. And so if you follow that all the way through, the sum over all intervals is about 119 or 120. And what Conrad did is, and maybe the quickest way, is to look at all your intervals and just average them and then multiply by the whole time interval. So if the average is 40 or 45 kilowatts and you multiply that by 2.5 hours, you'll get the total power consumption for this time period. Does this make sense how you could take this information and apply this calculation for 100 data points or 1,000 data points? It's the same process either way. Okay, so the next thing I want to know is what is the demand, assuming
I had a quick comment on that last.
Yeah.
Just kind of a point of distinction that I was thinking about. This doesn't represent the actual energy they use because we're taking 15-minute approximations. It's like a trapezoidal rule, like integration. So I'm not sure if the electric companies are, because they have like a totalizer meter, I think. So their energy use might be different than what this 15-minute data use would get. I don't know if anybody has any knowledge about that.
I honestly do not know, but I think the point is we're trying to simply differentiate here between KWH and KW fundamentally.
Yeah, I can't speak to that either, Jake. I agree. This does assume that you have the exact average power. I don't know how big of a difference you would have in those terms.
I guess if you were to do this and you get some sort of different energy from what the bills say, that might be a reason why. So just if that happens to anyone.
Yeah, and I don't know if Blake can speak to that, but he might have mentioned with some assessments that, and oh, sorry, I was supposed to mention this. If you guys have any questions, don't mention any clients by name. But Blake might have looked at some power consumption profiles that didn't exactly match up with a client's data in their bills. I'm not sure if that would be the case, why. But yeah, there may be different ways in which the 15-minute average data gets calculated compared to the actual power meters. But for this simple case, if you just assume we have the actual 15-minute average power, then you could extrapolate it this way. At a minimum, it should give you a good ballpark idea of what's happening. I don't know how big of an error you could potentially have.
Yeah, Derek, if I can comment on that, but we found this, there was a discrepancy. It was even like, I think it was like 50 kilowatts, like consistently across the board for months, like for different months on the calculation of the bills for the demand charge on this particular assessment. And we caught it too late. We'd already turned in the assessment, but that would definitely be something that would be good to check if you have this interval data, right? Check to make sure the monthly highest average is what they're being charged for. And if it isn't, it'd be something we should check with the utility to see if they need to recalibrate their meter or whatever they need to do. But it'd be interesting to check that.
Yeah, thanks, Blake. Do you have a guesstimate on the percentage of the demand that was?
I'd say it was probably 15 to 20%. Even I calculated the savings. It was like $1,200 a month. If it was off, then they were paying an extra $1,200 a month.
Wow. Okay. Well, that's I guess that's good to know.
Yeah.
All right. So the next thing is for billing purposes with this interval, what is the demand for this 10, 15-minute intervals? Or can anyone tell me what demand is as far as billing purposes go?
So it would be the highest demand out of any of these 15-minute intervals. So in this case, it'd be that block number 6.
Awesome. Thanks, Nestor. Yeah, so that would be 93 kilowatts. So it's just looking at it and taking the highest value. So 93 kilowatts. Okay. Now, with a demand of 93 kilowatts and the total energy consumption over this time interval of 119 kilowatt hours, what is the load factor of this data set? Or how do you calculate the load factor?
So load factor, I like to think of it as like how equivalent your demand use is. So if you're using the same demand all the time, you would have a load factor of 1. So the equation for that would be, it's the average demand divided by your peak demand.
Awesome. Thanks, Conrad. All right. I don't know how to get people to participate that haven't participated, but if anyone is shy about participating, this is really trying to get people to kind of get these fundamental concepts kind of ingrained, because load factor shows up in every single report, demand shows up in every report, total energy consumption shows up in every report, and it's pretty critical that we understand it. So yeah, like Conrad said, he explained the load factor using the expression on the right, average power over demand. But you can also think of it as the total energy divided by the demand times the time interval. Won't make you guys calculate it out, but you can kind of guesstimate it just by looking at it, that the average power draw compared to the peak power draw is about 50%. And if you actually do the math out, it's about 0.51. So this load factor, that means on average, they're consuming about half the power that they do at their maximum power draw. what does a high load factor mean? Or what does a load factor of 1 mean?
Doesn't it mean that their power draw is pretty much consistent throughout the entire day? Like
Yes,
doesn't fluctuate at all.
exactly. It's basically they have the same power draw all the time. And so alternatively, the low load factor means that they're oftentimes consuming very little energy with really large spikes in their demand. So if you were at a facility and you were interested in lowering their demand, do you think it'd be easier to lower the demand at a facility that has a low load factor or a high load factor? Obviously, there's an it depends in there, but just thinking about how we lower demand. I'll just, so lowering the demand with low load factor is usually easier because if it's a high load factor and they have a consistent power draw all day long, to lower their demand, you'd have to fundamentally change their process in some way that to make it more efficient or lower energy consumption, but you don't have the flexibility of changing around their process because it's running all the time. Instead, you actually have to lower the energy consumption at every single time interval. However, for a low load factor, that means you have these occasional random spikes in power. You have a little bit more flexibility. You could make whatever process is causing that spike more efficient. You could also have the flexibility to maybe move that process around. Maybe it's a batch process that they're running in the middle of the day. Maybe they could run it at night. All right.
Hey, Derek,
So-
I just want to tag on that and not name names, but
Did Julie just freeze? Or did I freeze?
Yeah, I think she froze.
I was worried that was me for a second.
Okay. Sorry, Julie, you froze. I'm just going to keep going for now. All right. So really what we're interested in with this 15-minute interval data is looking at the patterns of the power consumption. It gives us an idea, kind of half the picture of what's happening at these facilities. So these two power consumption profiles have the exact same load factor. If you were looking at these power consumptions, is there anything that jumps out to you if you saw this for a facility? Does one of these look like it would be easier to lower the demand, or can you think of any processes that might fit this? This is still just only 2.5 hours of data, but it's you can start to think about what processes might be happening here.
On the first one, if they could maybe change a shift and change half of their second half operations to the first half, then that would effectively cut down half of their demand.
Awesome. Yeah. Thanks, James. Yeah. Like you said, that's definitely a candidate for something to look for. Are there 3 processes that can each consume something like 15 kilowatts of data from time interval 6 to 10, and we could move one of those maybe to time intervals 1 to 5 and move that over. That might be a good thing. Or for the second one, where we have these spikes every 15 minutes, is that just a compressor that's turning on for some weird reason in this very basically perfect pattern, or is that batches all being turned on? We see this power consumption, and we don't really know, but we start having ideas of potential ways to lower the demand because we know where the demand is, and so we start thinking about how to move it around. We want to match this up with the process, but just by looking at it, you can start looking at some patterns. And there's one other idea I want to point out, and that's base load. So base load is kind of the minimum constant power draw that a facility experiences. Often this is at night when they're not running everything. Or so the base load is more of just maybe a vocabulary term, but it's just the power draw that's just always present. You'll basically never be able to get rid of it. Maybe by replacing lights or something, you can lower it, but it's basically the ever-present power draw of the facility. All right, so now I just want to kind of expand out looking at this data on larger time horizons. So moving from 2.5 hours to a whole day's worth of data, you can see that this is just one day. This is actually a weekend. But the power draw of this facility for this one day is pretty stagnant. It's not very exciting because it only ranges from 680 kilowatts to 880 kilowatts, maybe not even that. And but you can start seeing that there's these different patterns, and maybe earlier in maybe that last time interval was just the 37 to 47, that lull in the middle of the day. But if we're interested in minimizing demand, we want to know where that maximum power draw is at. So we need to keep expanding these time horizons to really understand what's happening at the facility. So if we expand it to a whole week, then maybe we can see what's happening at this facility. Does anyone have a guess on where the weekend and weekdays are with this facility?
I'd guess the weekend starts at about 577, somewhere in there, and then the weekdays are 25 through 97, and then kind of when it falls, that same pattern.
Nice, yeah. So yeah, you can, just by looking at 1 week of data, you can see that these patterns start to emerge. During the week, they have 5 consistent work days, which is not uncommon for manufacturing facilities. And then during the weekend, they have what looks like just their base load. And if you're trying to reduce their demand, where are you interested in looking? So as I mentioned, demand is usually during weekdays, during on-peak hours. And so we can see that in this case, that aligns with kind of the major power draws at these facilities. And so we want to look at what processes are happening in the middle of the day during the weekdays, because that's when their maximum power draw is occurring.
And it looks, what I'm noticing here in this pattern is that it looks like on their weekdays, they're very front loaded. So they get to work, they start something in the morning, and then, assuming that's maybe 8 a.m., it looks like their major power draw is set somewhere between, maybe 8 a.m. and 12 p.m. And then kind of in the afternoon, they must have something shut off because their afternoon is much lower than their morning on a work day.
Awesome. That's a really detailed observation, Michael. That's great. Yeah, so just by like what you said, just by looking at these processes, you can start to maybe not get full conclusions, but get some ideas about what's happening at these facilities without knowing anything about the process. And yeah, so these weekday peaks even have 2 separate things happening, like Michael said. And so you really want to know what's happening, what's being turned on at those times. These are it helps you come up with maybe some targeted questions for these facilities before you go there. So you can kind of see what's to blame for these high demands and kind of figure out what is possible to move around. Maybe they have to run certain things at very specific times, but we want to see this data to figure out to be most effective in our demand reduction. All right, so we can expand this out to a month, and you'll see that the pattern persists on a weekly basis. And we've looked at time intervals of 2 hours, 1 day, a week, and a month. And each facility is going to be different, but there's certain time horizons that are probably really important to look at. It's the weekly basis. And, when you look at this monthly time interval, you can see that the weekly patterns repeat over and over again. And so that allows you to say, yep, the same thing's happening every single week. Let's look at these specific processes that are happening on weekdays for this facility if we're trying to reduce the demand. So yeah, looking at weekly and monthly time horizons is critical. One other thing you can do with the data is overlap this is a different data set. This is from ASU's presentation on 15-minute interval data from the director's meeting this summer. But one thing you can do is overlap 15-minute power draw data for every single day of the week and see how consistent they are every single day. In this process, it looks like their power draw is basically the same every single day, which to me indicates that the process is pretty rigid in how they're functioning. There's not all that much flexibility in what's going on. If you plotted the daily power consumption or the average power consumption throughout for a manufacturing facility for different days of the week, and there was a huge spread in what was happening. Mondays were really low and then Tuesdays were really high. That would immediately indicate that there's some sort of opportunity or some questions that need to be asked about, why are you running certain things on Tuesdays and Wednesdays, or how do you select when to run different processes? So I think very generally speaking, when it's really a tight overlap like this, the process is probably pretty tightly controlled and managed. But if this spread is really wide, then there may be opportunities for us to think about what decisions are being made in the process. All right. So now this is kind of thinking a little bit in terms of minimizing bills. So for this facility, this is going back to just a one day at a facility with on-peak hours shown in the light red. You can see that the maximum power draw at the facility occurs during on-peak hours. That maximum power draw is approximately 2,000 kilowatts, something above that. If we want to move a process around, where do we want to move the process from and where do we want to move it to, if there is such flexibility? So you have a process that's happening from 8 to 12, as Michael kind of observed earlier with that weekly power draw data. Do we want to move it more into on-peak hours or away from on-peak hours?
You'd want to move into off-peak hours.
Awesome. Yeah. So that's kind of just a solid approach, is we want to think about how we can run processes during off-peak hours, if that's possible. I mean, it's not always possible at a facility, but we want to ask questions, what are the limits? What are the constraints? What's keeping us from moving processes that are running during the times of most expensive electricity or most expensive demand, and keep moving those to different times of the day? And so just to think about on-peak or demand versus on and off-peak electricity, if we can shift a process, half off-peak and half on-peak, will that benefit lowering the demand or lowering the bill with on and off-peak electricity more? I guess what I want to highlight is if you have on and off-peak electricity, that means you have really expensive electricity during on-peak hours and much cheaper electricity during off-peak hours. Even just partially shifting a process outside of that on-peak window can save you a lot of money, even if you don't necessarily lower the demand. Because the demand is such an all or nothing game, you're really trying to either move the process entirely off peak or potentially keep it, move it entirely off peak to gain the benefit of reducing the demand. It's a little bit more challenging, but with an on peak and off peak electricity, you can do a partial shift and still see some savings. You know, if 50% or 20% of this process is run during off peak hours, you just saved a sizable chunk of money if you do that every single day.
And then for that partial shift would be energy rather than demand savings, right? Just because it's more energy that's off peak, or is that just okay?
Exactly. So you're not really saving. You're not necessarily reducing demand, but you are reducing your on-peak electricity consumption because you only need to move a fraction of it off in order to save money.
Derek?
Yeah.
I have a question. So when we do our ARs, we list the amount of demand the maximum demand of whatever AR we're working on. And then we use the rate for demand to find our demand savings. So where in the report does this come to play? There's a part where we see the on-peak demand and off-peak.
Just to clarify, you're talking about demand or on and off-peak electricity rates? So
is this where, like, do we get our demand rate from this analysis, or like this data on analyzing our demand during on-peak and off-peak hours? Do we use the analysis for our the demand rate for our report?
When you say demand rate, do you mean how much it costs in terms of dollars per kilowatt, or
yeah, like what I'm saying is, if we were gonna write a report, would this just be a separate AR, not relevant to the demand we have on our, like on other ARs? Like, would this be a separate demand AR?
Like load shifting would be the AR in this case. Sorry, I don't have a great answer for your question.
No, you're good. I was just a little bit confused on if this was done as well by the utility analysis. And I also had a question if, like, my other question was.
Can you hear me okay?
Yeah.
I want to jump in a couple things that you're asking. You're asking good questions that help to clarify. The first thing I want to say is, generally speaking, the data that Derek's showing here, we don't typically get it. It's unusual that we get this amount of demand data. Typically right now, what we're getting is a single point of demand from the utility for the maximum of a month. That's it. We're hoping to do more assessments where we have more data like this. So when you're talking about your ARs, at least to date, it's primarily been, you use the rate that the utility, the cost of the demand per the utility rate structure. There are some rate structures that have on-peak and off-peak demand. In that case, we'd have to determine if the demand savings, when that's occurring, and use the right rate, but that's been very unusual.
Yeah, I was just a little bit confused on that. Thank you for clarifying things. Yeah, my other question was what you just answered about where do we get this information from? But yeah, thank you, that answers it. Thank you.
It's good questions, because fundamentally what we're trying to say here is that historically we haven't gotten this level of data, but we're hoping to move towards assessments where we do. and we're starting to introduce the team to the concepts associated with that when we start to get more data. So I'm glad you asked it.
Awesome. Thank you, Julie. Yeah, I'm glad you could answer that question. Yeah, so this is just taking it one step further. If you move a process completely off from on peak to off peak, then now it's a candidate for reducing demand. And with this interval data, it's a lot easier to see that. But like Mateo said and Julie clarified, we don't always have this data, which is what I'll get into next. So Rocky Mountain Power is rolling out an energy profiler online, and this is something that James and Will are working on. And it's something, you know, for us, it would make our jobs a lot easier if manufacturing facilities had this. You don't always have the resources to do this because it does cost money, but it is something that maybe we can make the case that, you know, if you guys monitor your power consumption, it's going to be a lot easier for you guys to save money on your bills, or kind of point, you know, we're not necessarily advertising on Rocky Mountain Power's behalf, but more on kind of the idea that 15-minute interval data is really valuable for them. Other options that facilities have is to do their own internal monitoring. I don't know if anyone here went on the Bimbo Bakery assessment. That team might have all graduated. I didn't go on it, but they had smart meters at their facility. And
one of them graduated and came back.
Oh, nice. Yeah, so I assume Michael. Yeah, so you were there. I wasn't on it, but it was involved in it in other ways, and they put on their own meters. And I don't remember who it was, but the company came, or yeah, the utility came and gave a talk about how they can install smart meters on different machinery or on just their meters to do their own internal monitoring. So if companies don't necessarily want to go through Rocky Mountain Power, there are other options. But something Julie did point out is nationwide, these utilities offer, a lot of utilities offer this data. So it's becoming kind of a core, this 15-minute interval data and the analysis of it is becoming a core aspect of being an energy engineer. And it just really does give you a bigger picture and a more detailed picture of what's going on at these facilities. So today I really talked about like really high level stuff. Didn't talk about any ARs or anything super technical, just trying to get, you know, what do you do if you have this 15-minute interval data? Where do you even get started? What are some simple data points you can pull out? What are some patterns you can look for? But there are other ways to look into it. There is more information to look at. There's 2 IIAC presentations from the directors meeting, which I have the link here. It's available to everyone who can log into the IIAC database, and those are good. They go into a little more detail and a little bit maybe more technical. And I know Jake is going to hit on some of those topics next week, but I think our own Jake going into specific ARs next week and talking about how to actually use this data in a way that directly helps us write our reports in terms of demand savings and what to look for is going to be really useful. Kind of pairing these 2 presentations, the one from this week and next week together. So just to summarize really quickly, bills give you 1 data point for the demand of the facility, demand or demand charge and facility charge. And there's only so much you can do with that information. 15-minute data gives you detailed information, makes our job as energy engineers a lot easier, and it's becoming more common. So it's something, even if it's not ubiquitous right now, it's something that we should be comfortable with. We want to use this data to look for patterns and come up with ideas, ahead of time. You immediately start thinking of different ways to move around energy consumption after you see how it works at the facility. But ultimately, if you pair this 15-minute interval data together with the actual process, we ask the questions we normally ask during IIAC assessments, maybe a little bit more targeted with this data information, you can get a really good idea of how this facility consumes energy. What is causing the demand spikes? Where is their flexibility, and what changes could they make that would have a bigger impact? It takes a lot of the guesswork out of what we're doing. So yeah, that's all I have other than giving you guys a fun homework assignment. It's really, really quick. It's just an Excel spreadsheet and a few questions to answer. It's just 1 day's worth of 15-minute interval data, and just asking you to plot it, look at it, and analyze it through the lens of 2 billing rate structures. And hopefully you guys can kind of understand, look at that data and maybe come up with some, do some of your own thinking about it. But yeah, that's all I have for you guys today.
Sounds good. Thanks, Derek. I know we ran a little bit long, but this is a super important topic that we want to grow into. So I appreciate you getting the group conversation started, and look forward to continuing it next week.
Yeah, thanks, Derek. For those